Hello, everyone, and welcome to this IFST webinar, Seeing the Unseen, the Power of X-ray Technology to Enhance Food Safety, sponsored by Aishida. Founded in Kyoto, Japan in 1893, Aishida is now a global company with a turnover in excess of $1 billion and more than 3,500 employees across the globe. They're a family-owned business passed down over 5 generations. Aishida offers a wide range of weighing, X-ray inspection, check weighing, tray sealing, packing, and leak detection equipment, plus supporting software for food and non-food applications, such as hardware and tablets. My name is Natasha Medhurst. I've worked all my life in the food sector, including in international technical roles in leading manufacturers involved in dry mixes, canning, extrusion, and baking, for example. Currently working as the IFST Senior Scientific Affairs Manager, I'm responsible for overseeing trusted scientific resources for our members and other interested parties by engagement with our members. Today's webinar aims to remove the mystery behind X-rays and provides a clear and understandable explanation on the different levels of technology available and the benefits of each. This webinar is being recorded and will be uploaded to IFST's Webinar Hub. Feel free to make comments and ask questions throughout the webinar using the Q&A function, which you'd find at the bottom of your screen. This can be used also in the case of any technical difficulties. You can upvote other people's questions by clicking the like button next to their question. There'll be a Q&A session after the presentation where we'll respond to as many of these questions as is possible. IFST has a number of knowledge hubs, including the Food Safety Knowledge Hub, available via our website. The format of the knowledge hubs is to satisfy the needs of different user groups. For example, SMEs, larger businesses, and for individuals such as educators and consumers. The guidance for large food businesses, for instance, includes robust information about systems across the food sector. It's ideal for employees and consumers alike to understand much more about what is necessary. For example, food safety culture, so it serves as a valuable management tool. The guidance provided and signposted to is considered to be best practice wherever in the world you operate. Our speaker today is Glenn Oxborough, Quality Inspection Control Sales Specialist at Aishida Europe. Glenn joined Aishida Europe in 2015 and has been developing the Aishida X-ray product segment across multiple food sectors. With over 30 years in the food industry, he's focused solely on quality control solutions and is very familiar with the requirements and day-to-day challenges that producers face when choosing and successfully implementing the right inline inspection equipment. For more information on his biography, please have a look at the website. So with that, I'll hand over to you now, Glenn.
Thank you, Natasha. So thank you all for joining this morning, and I hope you find this webinar useful. As Natasha said, any questions you've got as we go through would be very gratefully received. So Natasha touched on the history of Ishida as a global business. Just a quick introduction to Ishida Europe specifically. Ishida Europe in itself is a long-established business back in 1985, so coming up to our 40-year anniversary. We employed 685 people throughout the EMEA region. And turnover of 158 million last year. Now, most people will know us for multi-head weighing and check weighing, but actually X-ray represents a major part of our business. And what many people in the sector might not know is we've actually been supplying X-ray into the European market since 2006. And we've actually been building X-ray machines in the UK for the last 6 or 7 years as well. So it's a market in which we are very, very active indeed. But it's not necessarily something the Ishida name is normally necessarily immediately associated with. Now, I don't want to get too technical too quickly, but when we're talking about X-ray machines, we need to understand a little bit about the theory. So, for anybody that's not familiar, this section is just a very brief overview on the basic functionality of how an X-ray machine works. Because we need to understand this when we start to look at the differences between the different types of models and the different types of technology that are involved. So in simple terms, a product enters the X-ray machine from an in-feed conveyor, passes through the X-ray beam, which is here. Beneath the conveyor here is a detection mechanism. So the detector receives the amount of X-ray that is passed through the product. That generates an image on the screen, and then software analyzes that image and looks for anomalies and foreign bodies within that image, and then a decision is made as to whether that product is good or bad. So in simple terms, that's how an X-ray machine works. Now, when we drill down into this, we get down to the component level. And in terms of hardware, when we're looking at different model types and different machines that are available on the market today, we need to have an appreciation of the different hardware components that are involved and the impact that they have on how the machine operates and the level of sensitivity and the types of foreign bodies that are going to be reliably detected. So the two main components for any X-ray machine are going to be the X-ray tube. So that's the item that produces the X-rays, and the detector. So that's what receives the X-rays and then creates the image that's on the screen. Now we're going to go through some of these in more detail as we go through the different machine types and the types that are available. But in essence, in terms of the X-ray tube, there are two main types available, either a beryllium or a glass, and we'll talk about the differences between those. And then depending on the model or the manufacturer or the machine type, then different X-ray machines will have different amounts of power. Excuse me. And the power of an X-ray machine is measured in watts. And if anybody remembers their school physics, will know that watts is voltage times current. So that power in watts is made up of the kV, kilovolts, which is the penetrative power of the X-ray. So how much power it's got to push through the product, and the milliamps, which is the quantity of the X-ray that's produced. Typically, for a thicker product or a more dense product, you need a higher kV to push through the product to get the right amount of X-rays onto the detector to create the image. When we come to the detector, the main point is that the detector size or the photodiode size that's contained within the detector is going to dictate the image resolution. And ultimately, the better resolution we have, the better results we're going to achieve. A smaller detector generally requires higher power, and we can have a single or dual energy response or even multi-energy response in terms of the detector. There are different types that are available that we'll talk about. There's a scintillator type and a direct conversion type, and we'll cover those in more detail. So these are the two main components that we need to be generally aware of when we look at different model types. So in terms of the scope of X-ray machines that are available on the market today, so we have a standard single energy machine, higher sensitivity single energy machine, dual energy, and the latest in innovation and the latest technology on the market, which is called direct conversion or photon counting. Now, as Ishida, we supply machines in all of these different segments, as do many of our competitors in the market. So whilst I'm be talking more specifically about Ishida in terms of the technologies, What we're talking about here applies across the broad spectrum of X-ray suppliers. So standard single energy machine, typically a glass tube type, and we'll come on to we'll come on to that as we drill down into this a bit further. Typically lower power machines, good for metal detection and high density materials. Typical applications for the standard single energy is typically end of line primary package product, generally where the customer's looking to achieve a set level of sensitivity, whether that's their internal standards or set upon them by their customers, be it a retailer or whoever, where they cannot meet those standards with a traditional metal detection system. So that tends to be metal detection replacement. Then we come on to a higher sensitivity single energy. So that's taking the standard single energy and advancing upon that to improve the detection levels that are achievable. Typical markets here are those customers with products that have a particular foreign body risk. So it might not just be about meeting that minimum metal detection requirement. There might be an inherent foreign body risk, say something with field harvested vegetables or dried fruits or something like that, where you can get stones or any kind of debris from the fields that might be lower density and more difficult to detect. And you can't achieve the level that you need to using a standard single energy system. Then moving up the technology, we come to dual energy systems. Now, the dual energy enhances the detection of lower density and more difficult to detect foreign bodies. So from an Ishida point of view, this type of technology we most often use in the poultry sector, looking for bones in chicken fillets, whether it's wishbone, thigh bone, fan bone, and these tend to be much lower density because of the age in which the chickens are killed. There's not much calcification in the bones, makes them very difficult to detect, and that's where the dual energy principle comes in and creates an advantage. And then moving on to the latest direct conversion or photon counting machines. So these are really now the pinnacle of what's available on the market and give significant benefit over dual energy systems in terms of the detection of lower density foreign bodies, and particularly in complex and overlapping products that we'll talk about more as we come onto those in detail. So standard single energy system. So this typically has what we call a glass tube. Now, the glass tube in an X-ray. So this is the as we touched on to start with. This is what produces the X-ray that passes through the product. And a glass X-ray tube is the most cost-effective in terms of the production process in making that glass vacuum tube. The downside of having a glass tube is that the X-ray has to physically pass through the glass before it can come out into the atmosphere and then enter through the product. And that creates a filter effectively. So a glass tube will by nature filter the lower energy spectrum. And there are some disadvantages with that, but it really depends on the foreign body. Standard single energy systems typically tend to be lower power in the region of 150 watts, down to as low as 50 watts. And the standard detector resolution is somewhere in the region of 0.8 to 0.4 millimeters. And that's something that when you're talking to different manufacturers, that's something that you need to understand about the detector resolution. And again, this will differ depending on the supplier. But typically, if we're looking at in terms of metals and stainless steel in particular, in most applications, you're talking somewhere in the region of about 1.5 times the detector size is to what's going to be reliably detected. So in our case, we use a 0.4 millimeter detector. So in most cases, we'll be detecting down to 0.6 millimeters, sometimes 0.7, 0.8. But that 1.5 times multiplier is a reasonable indication as to what might be achievable depending on the product. Typical applications for a standard single energy system, as we touched on earlier, primarily end of line primary package product. So smaller size retail packs, particularly because they tend to be lower power, you're not going to be putting secondary packaging or maybe even a large 20 kilo block of cheese or something like that through. It's really not suitable for those applications. Main applications are things like metallized films, foil trays, where traditional metal detection isn't able to achieve the results that are required. And typically for end of line retail compliance. So as we touched on to start with, standard single energy tends to be for those applications where we're looking to achieve a set standard, where we can't do that with a traditional metal detector. So this is a specific example from a customer. So the customer was a manufacturer of own label cakes for one of the major UK retailers. So their objective was to achieve better than the required standard. So they had confidence that they were being able to meet their commitments to their customer and to minimize false detections compared to the existing solutions they had on site. Now, you can probably tell from the image, if we look at this, you've got varying densities here. And that's because this particular product had a number of fruit inclusions, like a fruit type loaf. And because of those differences in densities, they were finding some challenges with the existing equipment that they had on site. So our solution to that, at least, was to provide one of these standard single energy systems on the end of line primary packaged products, so the individual loaf cakes. And the results that we were able to achieve on that, consistent detection down to 0.8 millimeters, down to 0.6 on occasion, and down to a 3 millimeter glass, 4 millimeter ceramic, which was more than enough to meet the customer requirements. So you might think, okay, what's the benefit of being able to go down to 0.8 when I need to get to 1.5? Well, this is where the issue around the false positive detection comes in. If we're able or you're able to source a system that is able to exceed your requirements by a reasonable margin, we then have a nice big gray area in between the capability of the machine at 0.8 millimeter consistently and what the customer target is at 1.5 millimeters. So that allows us to set the sensitivity somewhere in that gray area to give us 100% confidence that we're going to hit that 1.5 millimeter requirement each and every time, but be so far away from the actual performance level of the machine to ensure that the false positive level is an absolute minimum. So this is a really nice application for a standard single energy system. The detection requirements are basically industry standard. We can achieve those very easily with a very simple standard system. Now, if we move on to the higher sensitivity systems, so these are often in the same or similar applications to those for the standard single energy, but where the customer has a specific foreign body requirement, or they want to achieve the highest level of sensitivity that they can with a reasonably cost-effective solution. Now, a higher sensitivity system will typically use a beryllium tube compared to the glass. Now, we spoke before in the standard section about the glass tube. Here we have a beryllium tube. So rather than the glass where the X-ray passes through the glass, there's a window here made of a material called beryllium, and the X-rays pass through that window and then out into the atmosphere. And that's effectively invisible as far as X-ray is concerned. Now, you might be able to see the differences between the two images that we have on the screen here. The one on the left is taken with a beryllium window, and the one on the right is taken with a standard glass window. And this is both with exactly the same product. So with the beryllium, you can see we're getting a much clearer defined image, much better resolution around the edges of the product. But more importantly, or better to explain the difference between the beryllium and the glass, is around the edge, you can actually start to see some definition from the packaging, where we don't see that on the standard single energy system with the glass tube. And that's because the glass filters out the lower energy spectrum, as we've said. The beryllium does not. But then the lower energy spectrum is then starting to respond to the packaging around the system. So hence we're able to start to see that in the image where we're not with a standard system. And that's where the lower energy comes in. So those lower energies give us improved detection of lower density foreign bodies because the lower density foreign bodies respond better to lower energies than they do higher energies. And that has most advantage on thinner products or in bulk flow applications. So as well as being able to do the inspection on a final primary packaged product, you could also do that in a bulk scenario depending on what the application type is and what the product is. And we'll have some examples of those. The higher sensitivity type, typically higher power. In our portfolio, we run these machines between 150 and 300 watts. And they would typically have an improved detector resolution. So again, this will differ depending on which supplier you're talking to, but in our case, we have a 0.4 or even down to a 0.3 millimeter for the improved detection capability. So as we've said, primary packaged product with specific foreign body risks, typically lower densities. Bulk flow applications with a target foreign body cannot be detected in the finished packaging. So bulk flow, we tend to have a thinner layer, which improves the detection. If you're going into a larger primary package, you might not be able to achieve the required sensitivity there. And where enhanced value-added inspections are required, such as product areas in the product inclusions in the sealing area. So as well as using X-ray for the foreign bodies, which is obviously its primary function, you can also use it to add additional quality inspections. So if you imagine you've got a tray with a heat seal around the edge, you'd be able to use the higher sensitivity systems to pick up very small product inclusions within that sealing area because the low energies are able to respond to the sealing area and give us some definition around the edges of the tray that would not be achievable on the standard single energy systems. So a couple of application examples here. So this was a manufacturer of own branded chocolate biscuits. And they really wanted to achieve as high a level of sensitivity as was reasonably possible, as well as the ability to have additional quality inspections. So we can see here on the cake example, we were up at 0.8 millimeter. Okay, this is a different product, but we're down to 0.5 millimeter stainless steel. But what's more impressive is in terms of the lower density foreign bodies, we're down to a consistent ceramic detection of 2 millimeters, 1.5 millimeter glass, and then able to pick up much lower density materials such as Teflon and EDPM rubber as well. And we can see from the images here that we're also using in this example here the little blue dots indicate biscuits of the correct size and shape. And here we have one biscuit that's cracked and broken there that again the machine is able to differentiate. And again, as we said, you can see some definition from the packaging around the area there that would not be achievable on the standard single energy systems. Moving on to a bulk flow application. So this is a particularly interesting one. So this is from a coffee bean producer. And they wanted to achieve the best level of stone detection that they possibly could. Anybody that's involved within the coffee industry will know that stones are an inherent risk within that product. So they originally came to us and said, okay, we want to inspect our final bags. But they do up to a 5 kilo foil bag, which we can do, not a problem. But in the 5 kilo bag, we were able to achieve around a stone detection of about 3 to 4 millimeters consistently. And actually, they wanted to get down significantly lower than that. So what we proposed was rather than to do it in the final packaging, was to do it in bulk. So in bulk, we've got a thinner layer constantly flowing through the machine. And getting down to that layer, that enabled us to get down to a stone detection level of 1.5 millimeters, which actually is in the region that they wanted to achieve. So that's an example of not necessarily focusing on the primary packaging. That might naturally be the place where you want to install a machine, but actually, depending on what the foreign body is and the size that you want to be able to detect, it might not necessarily be the most effective location to do that. So that's a good example there. Moving on to dual energy. Now, dual energy is where we get a little more technical, and I will try and make this as simple as I possibly can. So here we see on the left, this would be a standard single energy system or a higher sensitivity system. So here we have our X-ray generator. This is our X-ray beam. Our product passes through, and we have a detector underneath. A dual energy system still uses one X-ray source, but has two levels of detector underneath. One responding to a high energy signal, the other responding to a low energy signal. And because we're using high and low energy, we can't use a glass tube, because as we've said, the glass filters the lower energy spectrum, and we need to utilize that with a dual energy system. So this machine uses a beryllium tube. So we take an image at high energy and an image at low energy. And the reason for that is different materials, as we can see from the chart down here, respond to different levels of energy. So when we produce X-rays, we're talking kV in terms of the power that's available within the X-ray tube. But when we convert those into actual X-rays, they're measured in keV, so kilo electron volts. So this is the energies of different keV, and this is how the different materials respond. So you can see with metals, regardless of where we are on the energy spectrum, against the baseline here, metals attenuate very well. So are easy to detect whether we're using high energy or low energy or either or. But when we get down to things like bone, up at the higher energy levels, where most X-ray systems, single energy systems work around the 60 to 80 range, there is a difference, but it's quite a small difference in terms of the responsiveness between the material that we're trying to detect and the product itself, which makes it very difficult to detect. However, when we get down to the lower energy side, whilst it is still relatively small, there is a measurable difference between the material that we're looking for and the background product. So that enables us to get some level of detection of those materials. But we can't run the machine at this level on its own because we're not going to getting enough penetration through. So what we do, we generate two images, one around this area, one around that area, subtract one from the other, and we're left with the foreign body. So typical applications for dual energy. Primarily, the main application, at least for Ishida for this technology, is bones in protein and mainly chicken. That's certainly from our point of view, our biggest market for this type of application. But there are some additional benefits in dual energy for some overlapping and complex products as well to enhance the detection levels of lower density materials. So this is an example of a dual energy system. So this was a processor of poultry fillets. So this wasn't a site where they processed themselves. They bought in material and then diced and trimmed or whatever, and then sent that on to further processing. But they wanted to inspect the incoming raw material, make sure it was bone free before they then sent it on for further processing. So here we can see some examples of the bones. And here, in particular, you can see that there's not much in the way of real density difference between the bone that we're trying to detect and the background product. And that's really where the enhancement in dual energy allows us to be able to pick those items up that would not be achievable on either the low energy, the standard single energy system, or even the higher sensitivity system. For products like this, we really need to use the dual energy. So in this example, we're running two lanes of fillets through the machine. Those with potential bone still remaining are then rejected onto a return conveyor that are then dropped down here, and then those can then later be reworked and then passed back through the system. So that's an example of a dual energy application. Now, if we move on and look at where we are in terms of the latest technology, so we can then talk about direct conversion or photon counting, as we refer to it. Now, all the machines that we've spoken about up until this point use what we call an indirect conversion process. So the detector that we've spoken about doesn't actually, excuse me, doesn't actually measure X-ray as such. What it does is that as the X-ray passes through the product, and then when we get to the surface of the detector, there's a material called a scintillator. And what the scintillator does is it converts the X-ray into visible light, and then a photodiode or a row of photodiodes that make up the detector will then measure the amount of visible light that's produced and then use that to create the image. Direct conversion doesn't use that process, so it removes the scintillation process. So with the scintillation process, we're adding some additional noise into the image. And then by removing that process, we're getting a much more clearly defined image at a much higher resolution. Now, the benefits of that are a much clearer, more defined image, as we've said, but also it's a scintillator that's the wear part on these traditional detectors. So you actually get a much longer life from the detector as well. Much higher resolution than any of the machines that we've spoken about up to this point, and the ability to measure the amount of energy of each X-ray photon to improve upon the existing dual energy processes. So typical applications. So this is a new technology, but we are seeing real interest from the amount of improvement that we were able to make in the poultry sector and protein sector generally in terms of bone detection. So whether that's in poultry or fish or other proteins. The other market that's opening up is complex and overlapping products. So if you imagine something like French fries, so a bag of frozen French fries, you have many different densities, overlapping shapes, the potential of a vertical fry in the pack, all of which can create false positives. And then because we don't want false positives, we have to reduce the sensitivity to accept those, and that then compromises the amount of detection levels that we're able to achieve. And this technology really does help to overcome that. And the lowest possible detection of metals in particularly high risk products. So that might be something like infant feeding or something like that. In standard systems, as we've seen, we're able to get down to 0.5 in some cases, 0.6, 0.7, 0.8. The smallest test piece that is available is a 0.3 millimeters, and the direct conversion or photon counting is able to get down to that 0.3 millimeter in many, many cases. So this is some examples comparing the different levels of detection that's achievable. So this is the IXPD, which is a direct conversion system. This is our GN system, which is our high sensitivity single energy system. So not the baseline, but the next one up. So here we're on our 0.3 millimeter ball, as we said, where we're detecting 0.5. Quartz glass at 3 millimeters down to 1.5. And here we have some aluminium. So these are plates at 0.5 millimeter thickness. And here we can see they're not even visible on the image. So impossible to detect with a standard system, but we're able to get down to a 2 millimeter diameter, 2 millimeter diameter plate at 0.5 millimeter thickness. So very impressive results. What's probably more impressive, we spoke about complex and overlapping products. So this is something like, this is some frozen vegetables in a bag. So we can see again, many complex and overlapping densities and shapes. So challenging from a traditional X-ray point of view. And this is an EDPM rubber. Again, smallest test piece we have is down to 3 millimeters. And you can see the densities here. There are other areas in the product that are clearly more dense than even the largest part, but yet the machine is able to differentiate those down to 3 millimeters. This is an example of looking at the same technology in terms of chicken and improved detection there. And again, from a fishbone example, again, these are items that would not normally be able to be detected with any of our existing systems. The fillets and the chicken one is an example of our evolution from our dual energy systems. We originally started with a G2, we moved to a G2E. Our current iteration is the G2F, but we can see the PD takes that level of detection for the different bone sizes and different shapes. You know, it's a substantial improvement. So in terms of a quick summary, and I appreciate there's a lot to take in here. Um, the main takeaway, I think, for me at least, is that there are a wide range of different technologies available within the X-ray market. I think it's often the perception that an X-ray machine is an X-ray machine, and that's not the case within the Ishida portfolio, and it's certainly not the case within the wider market. There are a range of different technologies that are available to suit different applications and different customer requirements. Detection capabilities depend on the level of technology employed. Well, that would probably go without saying. From a customer point of view, I think it's important that when we're talking to suppliers about X-ray machines, we need to be as clear as we can, or at least to have given some thought to what foreign bodies we need to find, what's inherent within the product, what contamination risks do I have, where do they come from, and from a food safety point of view, what sizes do I need to detect those at? So when we're talking to suppliers, we know what we want to achieve, and that then helps the supplier to be able to match the technology level to what those requirements are. Detection levels will will determine the type of technology that's best suited, as we've just said, and the optimum location. So that's an example of the bulk flow as we saw earlier. And if you have the opportunity, test your product with the same foreign body samples on different machines at different technology levels to really understand which level of benefit each technology gives and what's going to be best suited for you as a customer. So standard single energy systems for compliance, specific foreign body risks may require high detection, dual energy for poultry and bones in protein, and the latest is the direct conversion of photon counting, and that represents the current pinnacle. So that's a lot to take in a short amount of time, but I hope that's been helpful. If there's any questions that I can help with, then please feel free to ask. And I'll hand back to you, Natasha.
Fabulous. Thanks, Glenn. Really interesting, really engaging, and also useful to hear the different types of technology, the different applications they're suitable for, and how everyone can consider these for food safety risk management. So we're now moving on to the Q&A session. So moving on to our first question, Glenn. If a company is installing X-ray as a critical control point, CCP, can they move away from traditional metal detection entirely?
That's a good question. And really, without wanting to dodge that, it really depends on the application. We have many customers that have replaced metal detection with X-ray and now use X-ray as the CCP. We also have customers that have maintained metal detection within in the process and maintain the metal detector as their main critical control point. The reason for that comes down to really what the foreign body risks are. Metal detection and X-ray are fundamentally different technologies. They perform different functions. They do different things. So I think the best way to sort of think about this is if you've got a good example is a metal detectable plaster, your standard blue food industry plaster. That has a foil strip that runs all the way through the content of that plaster. There's enough foil content there to trigger the metal detector. But because X-ray is looking at individual points, there is not enough point of specific density within that very thin micron foil layer for X-ray to detect. So that would be picked up by a metal detector and not by an X-ray. There are X-ray detectable plasters that are available that have tungsten in them, which then enhances the detection for both metal detection and X-ray. So the point is that if you've got something that is going to be very fine or very thin, where it creates an overall volume. So a metal detector example, on an X-ray, you might be able to detect 0.8 millimeter stainless. Your metal detector might be picking up 2.5 millimeters. So you might think the X-ray is much better. I only need the X-ray. But if you take that 2.5 millimeter sphere, grind it up into a powder, distribute that through your product, you put that through your metal detector will still see it because you've still got 2.5 millimeters worth of stainless steel in that product. So the overall conductivity effect is the same.
Interesting. I didn't realize if it was broken down, it would be equivalent to the original solid. So that's very interesting.
Yeah, because then from an X-ray point of view, when you've done that, no one point is bigger than 0.8 millimeters. So therefore the X-ray doesn't see it. So it's about understanding what the risk is in the process and then which technology is going to be best suited. An X-ray will pick up a smaller individual piece over a metal detector every day of the week. But as an overall effect, the metal detector will, has some advantages because they work in different ways. So it really just comes down to understanding what the risk is and what the foreign body is that you're looking to see. I know
Absolutely.
that's a
No,
long way of answering, but
well, it isn't straightforward, and you've explained that. So it's about the situation. So it needs consideration. That's clear. Thank you so much. So the questions are coming in nicely. So you talked about bone, and the question here is about whether dual energy X-ray can detect cartilage as well.
um, cartilage is car ultimately cartilage isn't bone. And it doesn't have any degree of calcification. What we often find is we often detect cartilage where it creates an anomaly within the image. So we reject it not because of the cartilage itself, but of the way that it's affected the product around it within the product, if you see what I mean. But also there can often be on cartilage a small amount of um, almost like bone or marrow or where there's enough density there to for the dual energy to work. So can we detect cartilage with dual energy or photon counting for that matter? Sometimes, but it's not something that you would normally guarantee. And I don't believe there's any supplier out there that would be able to guarantee cartilage because best will in the world, you need some level of calcification within that to enable the machine to work.
Okay, that's clear. Going back to the comparison of metal detectors with X-rays, would you say it's down to better sensitivity? Would that be the main choice or reason for choice?
Um, I think ultimately it comes down to foreign body risk and what's inherent within the product. So by their very nature, metal detectors are going to detect metals. An X-ray system is going to detect a much wider range of foreign bodies. So if you've got a risk of bones from proteins or debris from field harvested products or dried fruits or anything like that, anything that has an inherent natural risk of foreign bodies, then an X-ray is going to have a significant advantage because by their nature, metal detectors are not going to see those. The other thing to consider is from a metal detection point of view, stainless steel is the weakest point as far as a metal detector is concerned. So you'll be looking at ferrous, non-ferrous, and stainless steel. And always stainless steel is going to be the highest level test piece or the largest test piece. That's not a factor with X-ray. because actually the density between your ferrous, non-ferrous, and stainless steel test pieces are very, very similar. So what you can achieve on ferrous and non-ferrous, you'll also achieve on stainless steel. So your X-ray will 99% of the time, if not 100% of the time, will give you a significant advantage in your stainless steel detection levels over and above a metal detection solution. Which is quite interesting, really, when you consider that stainless steel, in terms of food processing, is probably the most common metal.
Yeah, absolutely, in different shapes and forms. Okay, that's clear. Thank you. And then a specific question later on in your presentation talked about the different models of machines. So if you could just define, if you're able, the best model for pharmaceutical blister packs.
Um, we actually have a specific machine in Japan for blister packs. It's a variation of our higher sensitivity model actually. So as well as often the thing with blister packs is you're looking for the presence of the tablet and to ensure the tablet is not broken or or missing.
Mhm.
So yeah, that would tend to be a variation of one of our higher sensitivity machines.
Okay, that's clear. And that it probably applies to the sachets, the vials, the other types of packaging format. And the second part of the question is about validation documentation. Is that something you'll provide?
We have worked in the pharmaceutical sector before. To be completely frank, the pharmaceutical side and the requirements, I've worked in this sector before, so I have some understanding around the validation, the IQ, OQ, PQ requirements that are required. Um, we would have to work with the customer to implement that. The pharmaceutical side is quite a small percentage of the Ishida business. We are very much a food focused company. Technology can be employed within the pharmaceutical sector. We have done that before, but we would need to work with the customer rather than providing that as 100% service.
Okay, so it's about customer relationship and different trials and different expectations. Moving on to specific types of foreign matter, um, the questions around different types of insects, even as small as ants, but also about hairs, human hairs, rodent hairs, etc., I expect. So, did you want
Yeah,
to make a comment on that? Very fine particles.
I think that's quite a common thing. When we talk about food, we're effectively talking about organic matter. So that's our background product. And when we're talking about insects and things like that, we're also talking about organic matter. So what we're trying to do is find organic matter within organic matter. And generally, that's not achievable. Where we have had success in the past is where we have something that's, larger. So things like, we've had requirements in the past for rodents or slugs or snails within packed salads and things like that. And then, yes, they are organic matter, but they have a massive density because they're almost liquid, if you see what I mean, against a less dense background product. So that makes them detectable.
Mm.
But things like, small insects and hairs, organic matter in an organic product yeah, that's not achievable, unfortunately. If it was, we would be a very rich company indeed, I'm sure.
Yeah, that's something for the near future, maybe. So typical applications. We've spoken about different types of foods, and this is a specific one about fruity jams and condiments packed in glass jars, whether there's any opportunity for detecting fruit stones and stalks or any broken glass or any metal. I mean, metal's been spoken about, so maybe you could just focus on the latter. Again, it's organic and broken glass would be useful.
Yeah, that's an interesting one actually. I mean, that's It's a market again that I have prior experience of. It's not a market in which Ishida specializes, but I can answer the question. When you're looking at glass jars in particular, fruit stones and stalks, you're not going to find because you're looking for again, jams and things like that have a relatively high density, and the density of the fruit stones and stalks is not going to be sufficient to be able to see. And when we look at glass, metal is obviously easy, but glass becomes quite interesting because when you look at a glass jar, generally the foreign bodies are going to be at the base of the jar because of the weight of the foreign body against the product. Naturally, it has to be more dense than the product to be able to see generally. So they're naturally going to be either the jar's going to be broken in the filling process, or or whatever. The foreign body is going to be lower within the jar, and then you have the punt on the bottom. So the punt creates quite a big blind spot. So you need to have multiple beams looking from different angles to actually see around the punt to get a reasonable level of glass detection. It's certainly achievable, and there are systems on the market, and I'm happy to sort of talk and advise on that, but it's not something that Ishida do within our own portfolio.
I understand, and there's so many complications about different sizes and thicknesses of glass jar that would probably add to those discussions. Um, this one is around the false positives. So how does dual energy translate into false detections? And that would translate into slowing down production.
Um, that depends on the application and the level of sensitivity that's required. As with any X-ray system, the higher you want to run the sensitivity, the higher the probability of false detections. So if we talk about poultry as a specific example in this case, so if you're running, say, twin lanes as we saw in the presentation, and maybe 120 fillets per lane, um, typically to get a good level of bone detection. And it's more for rib bones and fan bones and things like that that are more difficult to get a high detection probability of those. You're probably looking at a false positive level in that application of somewhere in the region of 1 to 2%, I would say. But that product is then rejected to the front. So you've then normally got an operator at that point trimming that product, taking out any bones and passing them back through the system. So does it slow the production down? In terms of the machine itself, no. The only thing that would potentially slow it down is not having the resource in place to do the rework that would be required of the rejected product. So the X-ray itself wouldn't slow the process, but how the overall solution works as a whole would possibly have the potential to, I suppose.
It's just a factor that needs to be built in, doesn't it? So the most important is to make sure we've got control over the food and the safety. There are other questions, one about shells on nuts and one on AI, but I really think, particularly the latter one, AI, unless you can do it in one sentence, which I doubt, I think we'll probably be struggling with time on that one. Do you agree, Glenn?
I will make a quick note on AI. AI is something that we are looking at as a business. We have some AI capability on our latest dual energy and our latest photon counting machines. So yeah, I think that's a really interesting area of the market, but that is quite a wide conversation. But I will just touch on that to say, yeah, AI is something that we are actively working on as a business, and already have some solutions in place.
I'm sure. So that's a really good point to end on because we're talking about developments for the future. And in the interest of time, I'd just like to thank you again, Glenn. It was fascinating. For those of you who didn't get their questions answered, the speaker details will be included in the certificate of attendance that you'll receive by email after this event. The recording will be shared, including the Q&A session, to everyone who attended and ultimately will be on our webinar hub. There'll be a short survey, so please hang around as you can for a few minutes just to be able to complete that in, because it's really valuable feedback for all of us and ideas of how we can improve going forward. I'd like to say thank you to everyone for attending today, and a huge thank you to Ashida for sponsoring this webinar. So I'll wish you all a good day, and thanks, Glenn.
Thank you. Thanks, everybody. Bye bye.
Bye bye.